Hello everyone, I am Waseem Hassan from University of Copenhagen and I will be presenting our work on using low frequency sounds to create non-contact sensations on and in the body. This work is done in collaboration with Asier Marzo from Public University of Navarre and Kasper Hornbæk from University of Copenhagen. So the idea of using low frequency sounds as a haptic interface started with a thought experiment of sorts. So we have the audio spectrum from 20 Hz to 20,000 roughly. The ultrasonic range in this spectrum has been used for delivering haptic sensations very successfully by using the ultrahaptic device. Therefore, we thought, what if we could use the other end of the spectrum for something interesting? Our initial search showed that there are some studies that have shown that we can guide emotions using infrasound. But at the same time, there were other papers that found this topic as controversial. It seemed interesting for us to check it out, and we wanted to see if we could control or dictate emotions. Unfortunately, we could not get any meaningful results or replicate the other studies successfully within this range. However, we noticed that if we move to the lower frequency sounds from 20 to let's say 200 hertz, and in that vicinity we can feel the vibrations through the air. This was a happy coincidence for us. We tried to find out why this would happen, and after searching for probable reasons, we found that it is most likely due to standing waves being generated in the room. So when sound is emitted in an enclosed room, the low frequency waves can bounce off of the surfaces and create interference back with themselves. This can create standing waves in the room. When the frequency of the standing waves matches the resonance frequency of the room, the amplitude of vibration increases. These frequencies are called modes. And the standing waves at different frequencies can create different pressure patterns throughout the room. So with each frequency, we can basically expect a different pressure pattern. These pressure regions can be perceived by users at different parts of their body within the room. So next we wanted to create an environment where we could create standing waves, and we built a specialized room for this purpose. In this slide, we can see the room. The video of the room is being played on one side and static images on the other side. We can see that the room is made up of MDF wood, which is very good at reflecting sounds, especially at low frequencies. There are additionally no obstacles inside the room and the dimensions are fixed. Special attention was paid to make the room acoustically sealed for frequencies below 200 by keeping the nooks and crannies less than 5 millimeters. This also keeps minimum sound leakage. We use the SVSSP 4000 subwoofer as a sound source. Next, we wanted to find out the modal frequencies of the room with the given dimensions. The standing waves at resonant frequencies or modal frequencies of any room can be calculated based on its dimensions. We calculated ours using the resonance frequency formula for a rectangular cavity, and we discovered that there were 14 modes under 200 Hz for our room. So at these particular frequencies, the room was resonating at higher amplitude than normal. After calculating the modal frequencies, we wanted to see their pressure distribution patterns within the room. For that, we use the Helmholtz equation for wave propagation with Newman boundary conditions. We solved this equation using finite element analysis, and we found out the pressure distribution of each of the 14 modes. In the chart for the pressure distribution, the red shows areas of high pressure. After calculating the simulations, we wanted to verify if our simulation results were correct. For that, we carried out two characterizations. First, we recorded sound pressure in the room using a microphone, and second, we asked human participants to report sensations that they perceived while they were experiencing these low frequency sounds within this room. For the quantitative characterization, we recorded sound at 45 different locations, and this was repeated for each of the modal frequencies. We wanted to compare these recordings or the pressure at these locations with the simulation results. The results of this comparison showed that the mean absolute error varies from 13.5% to 39.8% as shown in the chart on the left side. It might seem that the error between the simulated and recorded pressures is quite high. However, when we look at the comparison between the two, it is seen that we have low error at areas of high pressure, and areas of low pressure in the simulation have higher errors. In the graph to the right, the black dots represent the simulated pressures, which are higher than 80% of the maximum. And if we compare the same dots to the recorded area, we can see that most of the black dots in the simulated and recorded data have very low error. A key point to note here is that our focus also lies in the areas of high pressure where we can feel all the haptic sensations. We also looked at how the pressure changes from areas of high pressure to low pressure, and these trends are similar in both the simulated and recorded data. Next, we wanted to see the perceptual effect of these modes. For that, we conducted a user study with 14 participants. They experienced each of the 14 modes at two different locations. These locations are shown in the chart for each mode. And from this experiment, we recorded three kinds of data. We asked the participants to report the intensity of the sensation on a scale of 1 to 7, report the areas of the body where they perceived the sensation, and to verbally describe the sensations. The sensation intensity data shows that most of the participants were able to perceive the sensation. As we can see, most of the ratings are between 3 and 6, and only 8.1% of the people rated the intensity at 1, which is the minimum intensity value. We also looked at the effect of location or modes on sensation intensity, but statistical analysis showed no significant difference in that case either. The participants reported the locations of the body where they felt sensations. A combined view of all the sensations in the experiment shows that the feet were reported most often, followed by the trunk area. We also have data for each of the modes separately, but I think I will not delve into those details. What is more important is to see if the reported sensation locations are the same as the one predicted by the simulations. For this comparison, we had to compare where users reported the sensations and where the simulations predicted areas of high pressure, which are likely to induce sensations. The picture on the right shows the relative height of a user in the room. We can think of it as what would a person perceive if they were to stand in the pressure field shown by the simulation. To carry a meaningful comparison, we divided the body into 5 vertical segments and then calculated the sensations percentage for each segment. It is calculated as the sensations reported in this segment divided by the total number of sensations reported by a participant. In the current case, we can populate the sensation percentage according to user data. This data is for mode 7 only. For the simulations, we extract a cuboid from the simulated pressure fields. This is where the participants were standing in the room for mode 7. We applied the same procedure of dividing the cuboid into 5 segments. Here, the maximum height of the pressure region is restricted to the maximum normalized height of the participant, which was 183 centimeters. The pressure for each segment is calculated by averaging the pressure intensity in that region. Then the intensity percentage is calculated by dividing the intensity in that region by the sum of all intensities, so that the percentages add up to 100. We populate the current table with data from mode 7. We repeated the same procedure for all the modes. These charts show the percentages for the different segments for each mode. We then calculated the error between the two. The overall result shows that there was a discrepancy of around 10%. It means that around 10% of the times users either reported a different location than simulation or did not report any location at all. In terms of describing the sensation in words, vibration and tingling was used most often, with 31 and 25 times. At the same time, pressure was also used 42 times. It means that along with vibrations, pressure was also a dominant sensation, which was kind of unexpected at the beginning of the experiment. Some participants used full sentences to describe their feelings, while others used short phrases, as we can see from the participant responses. We found two interesting trends in the verbal descriptors. We call these as the emergent properties of low frequency sound. The participants commonly reported that lower frequencies were strongly felt inside the body, whereas as the frequencies increased, the sensations transferred to the outside of the body more. Second, the participants also reported that the focal point of sensation inside the body became more focused as the frequencies increased, and that the lower frequencies had a widespread sensation. We did not anticipate these effects, but these can be used as guidelines for more targeted or tailored sensations in future studies or application scenarios. Using low frequency sound as a haptic interface is a new technology that we introduce in this paper. It is not very precise yet, but the current paper was about investigating if it was possible to induce sensations with this technology. This is also the first time that haptic device can provide sensations inside the body, and the interface can also be used to provide feedback to the whole body at once or parts of the body. The results from the user study can be used in combination with the simulations to devise an algorithm that can deliver predefined sensations. There were some interesting questions that we would like to follow up in the future. For instance, did the clothes of the participant influence their perception? Or why were the feet the most reported area? Is it because they were in contact with the vibrating ground and could easily grab the user's attention? And finally, why were hands not reported as frequently, although they are the most perceptive parts of the body? And with that, I end my presentation. Thank you for your attention.